Let me go live. Okay, we are live on YouTube as well. And let's start example 2.8. We have 2 points on a geocentric orbit, and altitude, and we have the true anomaly and altitude. Altitude of point 1 is 1,545 kilometers, and the true anomaly of point 1 is 126 degrees. Point 2 is I'm sorry, 852 kilometers, and theta 2 is 58 degrees. Okay, we are asked to find the eccentricity, the altitude of perigee, semi-major axis, and the period. And same as the previous lecture, what I'm going to do is to let you guys think about it a little bit. And whoever can guide us through the correct path will get a bonus point. Let me actually update the attendance bonuses right away. I usually forget about this. Steven. Nicholas, I'm assuming you're taking care of you're keeping track of your own bonus points, right?
Oh,
yeah.
Okay. Well, no, not 4 divided by 2.
So 2, yeah. 2.5 now, right? Okay, so.
No, that's
including today. Okay. You're too honest, man. Thank you. Do you have any ideas?
Yes.
Okay.
A while back, we used an equation to find the eccentricity. That was RA minus RP over RA plus RP, but we didn't know RA or RP, so we used RE and the others. Can we still use?
What is RE?
Radius of the Earth.
Radius R, the capital R.
Yes, correct.
Yeah, the radius of Earth is usually given. So it is 6,000. We are going to assume Earth is a spherical shape with 6,378 kilometers radius, right? So what Lawson is telling us to use is what is the equation?
It was RA minus RP over RA plus RP. Since we don't have radius of apogee or perigee, we just use the altitudes given. You have to convert the Z into RA and RP.
Okay. So we have two actually, I guess, opinions here that we're gonna do the Z1 plus RE minus Z2 plus RE, right? Divided by Z1 plus RE plus Z2 plus RE. Is this true?
Yes.
Let's take a vote from the online people as well. Is this true? Steven, I see you have a comment that says no. I don't remember what is that in response to. So, but do you have? Let's take a look about having questions. Okay, don't have any. Thank you. What do you think about this equation? Is this the correct way to go forward? We have 2 yes votes.
The last time we used it in the radius of apogee equation, we used the radius of Earth, but in the radius of perigee equation, we just used the different. We didn't use the same value.
Okay, we should have used the same value. But this equation is not the correct equation to use here. Why? Because Z1 and Z2 are not the altitudes of perigee and apogee. These are just two. I mean, they may be, but we are not told that they are the altitudes of perigee and apogee. And actually, we are asked, this should have given you the clue, right? We are asked to find the altitude of perigee, right? Which tells you that these two are not the altitude. And this discussion was the main reason I included this example. I just wanted to make sure that you are careful about this. Okay, so we cannot use this equation. And at this point, we are not able to find the radius of apogee and perigee because we have a lot of unknowns. We don't know eccentricity, we don't know the angular momentum, we don't know any of those, right? So how can we approach this problem? How can we solve this problem?
I mean, I'd like to project something onto the semi-major or the semi-minor axis, but I don't remember how to.
Let me ask you this. What was the orbital equation, the main orbit equation?
R equals
A squared over mu, 1 over 1 plus cosine theta.
Right? Is this correct? Do we have the theta? Yes, we have two thetas, theta 1. What about r? I mean, we do basically z1 plus re, right?
Yeah.
That's it. So we have the r for 2 points as well. Okay. Do we have mu? Yes, mu is the same. We have that was the value of 398,600, right?
And that's just a constant value.
It's just for f,
For
right? That's g multiplied by m2. We don't have eccentricity. We don't have h squared. What can you say about eccentricity and h squared for these 2 points?
Can you, eccentricity is also equal to h squared over rp mu. Can you put that in there and then cancel them algebraically? Or is it a lot simpler than that?
Let's answer my question first, right? You can do a lot of things. You can do a lot of simplicity. But what can you say about the h and e for these 2 points? How does h and e change between these 2 points? Okay, exactly. Igor is telling us that they are constant. They don't change for an orbit, right? That's we had the conservation of angular momentum, and eccentricity is just doesn't change for one orbit, right? So what does it mean? It means that if we plug in the numbers for these 2 points, we are going to have 2 equations and 2 unknowns, right?
where's the second equation?
One equation using z2 and theta 2, one equation using z1 and theta 1. So let's plug those in. We have 1545 plus 6,378 equals to h squared divided by 398,600 multiplied by 1 over 1 plus e cosine of 126 degrees. This will be your first equation. Your second equation is going to be 852 as a plus 6,378 equals to h squared divided by 398,600 multiplied by 1 plus e cosine of 58 degrees, right? These are pretty simple to calculate. We can find the two equations we need. And based on this, two equations, based on the system of equations, your eccentricity is going to be 0.08164, and your h is going to be 54,830 kilometers squared per second. Okay, so what kind of an orbit do we have?
Less than 1, greater than 0, not close to circular, but it's close to circular.
Elliptical, right? Yeah, but very close to circular. So what else do we need to calculate? We have already calculated eccentricity. We want to calculate the altitude of the perigee, right? How can we calculate the altitude of the perigee? We first have to calculate the radius of the perigee, right? R of p. What is R of p?
1 over, right, h squared over mu, 1 over 1 plus e.
That's it, mainly because this is essentially you put 0 here for theta, you're going to get that. And which is equal to z of p plus the radius of Earth. We have this value. We have eccentricity. We have angular momentum. We have mu. Your z of p is going to come out to be 595.5 kilometers. Okay. What about the semi-major axis?
Wait, that's just, oh, sorry.
What was the problem?
I thought you were RP, said ZP.
No, ZP here. The next part is asking us to find the semi-major axis. To find the semi-major axis, we had many equations, right? You are always welcome to use those many equations. But we can also find RA, or the radius of apogee, h squared divided by 1 minus e, right? If you plug in the numbers, your RA is going to become 8,213 kilometers. And we can find the semi-major axis, RA plus RE divided by 2, right? Which is going to be equal to 7,593 kilometers. And the last part is asking us to find the period. We had many equations when it came to period of the elliptical orbit. One of them was related to the semi-major axis. Just you use this equation.
2 pi over mu, a.
Yeah. Thank you. It will give you 6,585 seconds, which is equals to 1 hour, 1.829 hours. Okay, so the point of this example was to make sure what is given to you. This Z1 and theta 1, Z2 and theta 2 are not the perigee and apogee, right? You didn't even need to, I mean, I didn't even need to tell you that this is not ZA and ZP. Could have just looked at the thetas, right? Theta is not 0 and 180. Not the apogee and perigee. Okay. Any questions? Okay. So let's move on to the next example. Next example is telling us the perigee radius of a satellite in a parabolic geocentric trajectory of, there's also a figure given. Do you have the figure on your printouts? There's an extra one here for you, Nicholas.
I gotta remember to bring that sheet paper as well as the.
Yeah, that's. Is the figure there? I don't know. Yep, you have the figure there. We want to find the distance d between points P1 and P2 of the orbit, which are 8,000 kilometers and 16,000 kilometers respectively from the center of the Earth. So we have R of A, R1 and R2, right? But you want to find the distance d between them, which is given to you. Which is shown to you on the figure. How can we find this distance? What do you think we should do? But that will be the distance between the foci, right? And the distance between the foci, just to make sure we are clear, that's 2a is 2 times the semi-major axis. The distance between foci is smaller, right? Because foci is inside your ellipse. Let me just make sure. This is one focus, this is the other one, right? This distance is A. This distance was AE, right? So the distance between foci would be 2A. But what we want to find here is the distance between a random 2 points here. This distance, right? This is not the distance between the foci. Okay? So how can we find this distance? Azimuthal. How would you relate the azimuthal velocity to the distance between these two? How is this related to the distance here? R. Okay, so we are given R1 and R2, right? And this is essentially a triangle, right? We have this length, we have this length. We want to calculate this length, right? This is essentially the same thing. I've just rotated it. How can we find this length here? But then you have to find this distance, right?
We use delta theta.
Delta theta, okay. You are moving in the correct direction. How would you?
Way back, I remember that side angle side to calculate that second distance.
What's the equation you want to calculate? You want to use? Okay, so when you have let's see, do we have any online people who knows the answer to this?
It's like 8th grade geometry.
Okay, that's So it is very good that we are solving this. This distance d is going to be equal to the square root of r1 squared plus r2 squared minus 2 r1, r2 cosine of theta. In case of, what's that?
That wasn't mine.
I mean, you were talking about the sign relationships, but then we had to have this thetas as well. Otherwise, that wouldn't have been helpful. Have you ever seen this before?
Probably at some point. It's like a mix between the distance formula and something else.
Mix between the distance formula. Just take this formula if you haven't seen this. Okay. And I mean, in case this theta is 90 degrees, this will go away, and this will be the very famous Pythagorean theorem. Exactly. But if the theta is not 90 degrees, this is how you calculate this third distance. Okay. So we have this equation. We want to find this distance. How should we do this?
I would say plug in, but we don't have the theta value.
Exactly. How can we find that theta?
We use the regular equation, r equals a squared over mu, 1 over 1 plus e cosine. We have two r values. We have the eccentricity value. We have.
But we don't have the thetas, do we?
What we're trying to find.
Oh, where are we given the eccentricity?
It says it's concentric.
Oh, that's 0.
So,
It says it's parabolic, doesn't it? It's a parabolic trajectory. What is the eccentricity of a parabolic trajectory?
Parabolic is 1.
1. Okay. So you already know the eccentricity is 1. Okay, that's good. What do we have here and what don't we have here? We don't have h, right? And this theta 1 and theta 2 are different. So we have 3 unknowns. We cannot have the system of the equation. We don't. That's what we're looking for. We were looking for delta theta, right? But we don't have h squared. How can we find h squared?
Oh, wait. We have the apogee distance.
The perigee, right?
Sorry, perigee.
Yeah, exactly. So we have the perigee radius, which is going to be h squared 1 over e, right? 1. And that's essentially, it's a 1 plus e cosine of 0, 1 cosine of 0. This is 1. This is also 1. So this will go away. You will have this relationship for a parabolic trajectory, right? We have mu, it's earth. We have r of p. We can find the angular momentum, right? The angular momentum is going to be 74,700 square kilometers per second, which means that we can find theta. We can find theta 1 and theta 2. Theta 1 and theta 2 are going to be, theta 1 is 41.41 degrees, and theta 2 is going to be 97.18 degrees. That's it, exactly. So you just subtract the 2. So this is cosine of delta theta. If you subtract the 2, you're going to get 55.3 78 degrees. We have R1, we have R2, we have R1, R2. We can calculate this distance to be 13,270 kilometers. Is this clear?
What is that theta? So you said that theta 1 equals 41 degrees?
41.41, yep.
How do you find that?
We have the main orbit equation, right? Main orbit equation is h squared divided by mu multiplied by 1 plus 1 e cosine of theta. It's a parabolic trajectory, so E is 1, right? And we are given also R1, right? The only things we don't have here is theta 1 and h squared. How did we find h squared? Using this equation. We are given the perigee radius, we are given the mu. Mu is 398,600 for Earth, okay? So the only things which I assumed you knew from your background of mathematics, but I think you didn't know, which, I mean, that's all right. I mean,
We haven't done anything like that since, or personally, I haven't since middle school.
middle school.
Oh, yeah.
So you didn't have this in your like calculus, mathematics in his. What did you do in college?
Possibly did. Wait, a lot of limits and derivatives and integrals.
That's it. The only things you did was limits and derivatives and integrals.
Distance formula, which is why it kind of looks like distance formula, whatever that.
Not a lot of
We
trade.
did the siding and side thing that I was talking about, but we need two congruent triangles for that.
Okay. Okay. That's, I mean, but you have the equation now, right? If I ask you in an exam to find the distance between these 2 points and I give you R1s and R2, it's essentially one leg of this triangle, right? One, and you just have to find the theta here, plug it into this equation to find the distance. Okay. Any questions? This next one is also an interesting example. All of the examples we solved today were really interesting, to me at least. So I guess is the only thing that really counts, but I'm the one. Okay, example 2.10. Let me ask you one question. I'm thinking of giving you these type of questions on the exam, right? So the questions that needs a little, I mean, these questions are not that hard. They don't take that much time, but you have to have a little bit of creativity to be able to solve. You have to be able to think out of the box. How anxious would you be if you know that these are the type of questions you're going to get on an exam?
I'll take this over plug and chugging any day, I think.
Okay. But you always go for the harder route, which I appreciate.
I can,
But I think not everyone else in the class appreciates it.
I think I can work with it if there's like maybe a little hint to point in the right direction. Because if it's really open-ended, I don't want to spend 20 minutes, on a goose hunt.
I mean, it won't be open-ended, of course.
Yeah, but if it's a question like that, then and now that we've gone through it, it's pretty obvious which way to go. But like maybe like if you gave us that D like there, but then didn't tell us how to find the R's or the thetas, or that the thetas, or that there would be two equations with three different variables, that we would have to find A's or other stuff like that.
So like hits, have to use RP.
Yeah.
And probably be like decent enough for me to get through it, I think.
That's essentially the solution, though, right? If I tell you, I mean, this equation, I will give you as a hint, right? That's not the problem.
The assumption that you need to find R1 and R2. Well, not R1 and R2, but theta 1 and theta 2 to get.
So you like that type of a hint?
Just anywhere in the general direction.
Okay, that's it. What do you guys think? Trey, Nirlep, and the online student. If it's part of a If it's part through edge, it would be concerning. I'm not sure what are you. So Igor is saying if it's parts A through H, okay, it would be yeah. No. You won't get this many parts. I will make. I mean this. So example 2.10 has H parts, right? But these H parts are not as extensive as the ones you had in flight mechanics. So this is just one equation. But you will, if you get something like this in an exam, you will only have 2 problems to solve. Does this make sense? Yeah. Trey and Nila, do we have any input on the creative problems? Huh? You'll survive. Okay.
If it's the creative one, we only have to do 2.
No. If it's a 210, you only have to do 2. Like if it's a line problems. What do you think, Nila? Okay. That is also an acceptable position. Shorter. Okay. So let's continue this. Let's continue with the example. Do the online people have any other than Igor? I guess just some people just are there. You don't have any participation. I like the creative questions. Thank you. Yeah. I don't know what that means. What does this mean? I agree with Igor. Okay. You agree with whatever is saying up there. Okay. Okay, let's continue with example 2.10. It is telling us at a given point of a spacecraft geocentric trajectory, the radius is 14,600 kilometers. Okay. And the speed is 8.6 kilometers per second. So radius is 14,600 kilometers. And speed is 8.6 kilometers per second. Okay. The flight path angle is 50 degrees. First thing we are asked to do is to show that the path is a hyperbola. This is a hyperbolic trajectory. Let's actually do this first and then go through the rest of it. How should we do this?
If the eccentricity value is greater than 1, it's hyperbolic. If it is 1, it's hyperbolic. No, 1 is parabolic. Oh, parabolic is greater than 1.
Exactly. So eccentricity value has to be greater than 1, right? Can we show, so this is the first part of the question, right? I may not even ask you to find the eccentricity. Is there any other way to investigate whether this is a hyperbolic trajectory or not?
The angular momentum leads with more, or the angular, you know what I'm saying? It gets more energy.
Okay, how would you show that? Not with angular momentum.
Specific energy higher.
Positive.
Positive.
Okay.
That's what that. So we could find specific energy, and if it's positive, then it's hyperbolic.
Okay. So I guess what Nicholas wants to tell us that is the best way is to find the escape velocity as the first step. If your velocity is higher than the escape velocity, it means that you are essentially able to escape the orbit and continue your travel. You will have enough leftover energy to continue your travel, right? Your space travel. That was the idea, right? That was the idea of the hyperbolic trajectory. So how do we calculate the escape velocity? It was the square root of
2 mu over r.
exactly 2 mu over r. This was the escape velocity. What is mu here? 398,600, right? we are also given the r. Just plug in here. This is going to be 7.89 kilometers per second. What is the velocity? 8.6. So this velocity at this point, the escape velocity at this radius is lower than your velocity, which means that you will have some leftover energy to continue your space travel. And we are, based on this, since your escape v is larger than escape velocity, you have shown that this is a hyperbolic trajectory.
Pretty quick.
Yeah, it was pretty. Yeah, it is going pretty quick. Is that what you said? Yes, it is a space travel, so I
No
guess.
one's in a rush. I want to make a scene.
I mean, the radius of Earth is 6,000 kilometers, 7,000 kilometers, which is a very small thing in space. So 8 kilometers per second is not that much.
It
Right?
feels like I can imagine going 8 kilometers in a second. That'd be crazy.
Yeah, I agree with you. So let's continue. Angular momentum is the next thing they have asked us to find. How can we find angular momentum?
Equation. R equals.
Do we have theta? Do we have eccentricity? No. What do we have? So you always, before choosing the appropriate equation, you always want to come back to what is given to you. We are given the velocity, and we are also given the flight path angle. Okay? So how can we find angular momentum as a function of velocity? That's it. But not any velocity. That's the azimuthal velocity, right? Okay? So we have to find this azimuthal component of velocity, which we don't have. How can we do that? For your flight path angle is going to be equal to your azimuthal, your radial divided by azimuthal. Okay, but we still have.
V radial, is that 8.6 kilometers?
No, that's the total.
So we need to find radial.
Okay, what is the relationship between this V, VR, and V azimuthal?
You said V, VR, and V azimuthal?
Yeah, so these two are projections of V on the axis, on the tangential and radial axis, right? So what would be the relationship between V and those two components? V is going to be equals to a square root of VR squared plus V azimuthal squared, right? So we have the flight path angle, which is 50 degrees. We have this 8.6 kilometers. We have two equations, two unknowns, right? We can find the V radial and V azimuthal. Your V radial is going to be, V azimuthal is going to be 5.528 kilometers per second, which means that your V radial is going to be 6.588 kilometers per second. So we have the V azimuthal, we have the radius, right? We have R, and just plug it in to get your angular momentum to be 80,708 kilometers squared per second. Okay, what else? We are asked to find the eccentricity. How can we find the eccentricity here? This one is a little, just a little tricky. What is it though?
Escape velocity.
How would you relate it to escape velocity?
I'm not totally sure. If they both determine, or can determine that the orbit's hyperbolic, is there any way that they are related? Because I'm pretty sure this is one of the questions I was thinking was
Escape velocity is essentially the velocity of the parabolic trajectory, right? And which eccentricity is 1.
Does that say VS Mutual is 8.5 squared or 5?
5.5. This is 5. Not the best handwriting.
I think it would divide the velocities.
To get the eccentricity.
So you got escape velocity, I would say divided by the radial velocity. That's the curve, right? It's the velocity at which it curves.
But that will give you the flight path angle. It doesn't give you the eccentricity, right? Or 1 over flight path angle.
It's more than one, though.
What's that?
It's more than one, so it's a good guess.
Yeah. Yeah, definitely. It will give you a value of more than 1, which is also true about the eccentricity. But let's go back. What is the main orbit equation?
H squared over mu, 1 over 1 plus e cosine.
Okay, we have this, we have this, we have this, but we don't have any of this, theta or E. Do we have any equation for this hyperbolic trajectory that relates one of the components of velocity to eccentricity and theta? Let's see if we can find that.
V infinite equals mu over h e sine theta equals mu over h the square root of e.
So we are, as you said, is mu h. This is VR, right?
Yeah.
E sine of theta. So again, we have 2 equations, 2 unknowns. Right? Based on these 2 equations, we should be able to find the eccentricity and theta, right? But in the process of solving this, the only thing that may cause a little problem is this cosine and sine. So how should we take care of that? We are going to get e cosine of theta equals to, let me give you the numbers, the correct numbers. 1.33, let's do 1.3339. And e sine of theta equals to 0.11193. One way to go about it is to divide these 2 equations, get the tangent of theta equals to something, then you'll get theta, you can find eccentricity. Another way to go about it, just as your book has chosen to use, is to take them to the power 2, raise them to the power 2, add them up. You're going to get on one side e squared cosine squared sine squared, which is 1, to find the eccentricity, right? And this will give you the eccentricity equals to 1.3393.
Wait, so how did that work?
you have the values for E cosine theta and then you have E sine theta, and you square them, where did, how's that work out?
It raise it to the power 2. It's going to be this,
Yep.
right? This. If you add it up, you can take the E squared out. It's going to be E squared multiplied by cosine squared plus sine squared. Cosine squared plus sine squared is 1.
And then it has to equal the sum of those two.
Yes.
Okay, got it.
So you're saying that the square of 1.339 plus the square of 0.1193, square root of that is 1.3393?
This has to be a squared as well, right? It will give you E squared is going to be this squared plus this squared, right? Well, what I've given you here is just the E.
Might be a dumb question, but how'd you come to the conclusion that you should just add them?
But how should I? You want to simplify your problem, right? That's the goal. If I were to solve this, I would have just divided these two together, and then E's would have canceled out. Tangent of theta is equal to whatever, right? Find theta, find E, if I was to. But there's always other ways. You have sine and cosine. Whenever you have both sine and cosine, something that immediately should pop up in your mind is that sine squared plus cosine squared is 1. Can I produce that here? Yes. How? Just raise them to the power 2, add them, take the E out, right?
That systems of equation thing you can do.
You can also do the systems of equation thing, but then it is going to be a little harder. You have to have the sine squared, cosine squared. It is not going to be that easy, right? I guess the easiest path to go forward to find the eccentricity without any unrelated parameters. Here we didn't want to find theta. We wanted to find eccentricity, right?
I think I would have done the way that you would have done it. Found tangent theta, and then plug that back into the orbit equation.
Yeah.
That seems easy.
I
Yeah.
would have forced myself to come to this conclusion. I would have clung to cosine squared plus sine squared.
A lot of trig today.
What's that?
A lot of trig today.
That's orbital mechanics.
Yeah.
Orbital mechanics has a lot of trigonometry, right? And the other part C, is asking us to find theta. Okay.
Boom. Done.
You have the eccentricity, you can find theta. But one of these can give you, if you use the E cosine of theta, you're going to get 2 values for theta, right? In 2 different quadrants. Also for sine, you just have to make sure that you use both equations, right? And use the theta that is the same for both equations. I guess we have a little confusion here. Let's say just to make sure you are not confused. Yeah, your book way, the book's way is actually going to make this confusion. If you were to use my way, just dividing it up, it will be 1 tangent. You could have made that conclusion easier. But we have cosine of theta equals to a positive parameter, right? What is that? Let's say it is half. And we have sine of theta square root of 3 divided by 2. What is a theta here? 60 degrees, right? Right? Cosine of theta, sine of, right? Pi over 3. But for your cosine, we have pi over 3 and pi minus pi over 3 as well. It is going to be in the 3rd quadrant, right? No, it is in the 2nd quadrant. Why do you? and pi minus pi over 3, right? We have two answers for it. What about sine of theta? We also have two answers here. First one is the 60 degrees. The other one is pi plus pi over 3, right? In the third quadrant, because that's where cosine is. That's where sine is. Positive. It is the other way around, but you get the point. We have two different answers for all of these. Let's say your answer here is 60 and 240, right? And 60 and 120. Let's say these are the correct answers. What is your true anomaly? 60, because it is shared between these two. Does this make sense? Okay. Pardon me? Yeah, that's, yes, I guess that yeah, it's definitely easier. And not the easiest book. So next part is asking us to find the radius of perigee. How can we find the radius of perigee? Do we have the h here? Yes, we do. What is the equation for radius of perigee? H squared divided by mu. Let me write it up here. One plus 1e cosine of 0. We have the e, we have the h, we have the mu. We can find the radius of perigee to be whatever that value is. Let me give you the value. 6,986 kilometers. That's 986 kilometers. Did you have a question?
I was confused, like, how we got true anomaly to be 60.
It was just a random number.
That was just a random number.
So the correct true anomaly is actually, let's see, 84. Yeah.
How do we get that?
So we had e cosine of theta equals to 1.33 something, right? And e sine of theta equals to whatever, another value, which is 0.1193. We have the eccentricity. You can find theta, right? The point was, based on these two equations, you will get 2 theta from here, right? For cosine, it will be in the first quadrant and the third quadrant, right? So between 0 and pi over 2, between pi over 2, between pi and 3 pi over 2, right? For sine, it would have been in the first and the second quadrant, right? Your acceptable answer would have been the one that is in the first quadrant, because both of them will give you an answer there. Yes?
Could we have just done what you did with the tangent theta and then arctan of that relationship and just like that?
Yep.
And that will be the
So
true
much
anomaly.
easier.
Yep, that's right.
Okay, yep. Definitely.
Now, the reason is pretty simple. How does tangent go on your, how does tangent behave? Like this, right? Pi over 2, negative pi over 2. And then if you want to go to 2 pi over 2, it will be all like this, right? For tangent, you would have gotten 2 solutions as well, but that will be much easier to deal with. Does this make sense? And I mean, at the end of the day, if you give me 2 solutions, if you can find the correct solution, if you can't choose the correct solution out of the 2, you won't lose that many points. Just maybe 50% of the problem. And let's actually skip the semi-major axis, because I think you already know how to calculate that. The other part is asking us to find the hyperbolic excess velocity. How can we find the hyperbolic excess velocity? That's v, exactly. But if you recall, we just had the squared of this. Hyperbolic excess velocity is going to be is called v infinity s squared, which is v squared minus v escape squared. That's how we define it, right?
This is C3.
This is essentially exactly equals to C3.
Why is that notated as C3?
We talked about it in class. If you recall, you can always go back. But it is a very common notation. Let me put this way. There are some reasoning behind it, but not a very important part of the class. And then we have the turn angle. Did we talk about turn angle in class? We have one equation for the turn angle. I probably don't ask you to calculate the turn angle, but if I had to ask you, this is the equation you need to use. Turn angle delta, a small delta, is going to be equal to 2 inverse sine. I think we did talk about it. This will be the equation you need to use. If you have the eccentricity, you will be fine. And we also talked about the aiming radius, delta, the big delta, capital delta, which can be found using these two equations. So as long as you have the equations, you can find the correct equations. It's just plug and chug, right? I guess the only part of all of these examples that are very hard is the starting point. If you can start the solution, if you choose the correct idea to start solving the problem, you should be able to find answers to it. Okay, we have only 10 minutes left before the exam on 420. So I'm going to give you this option. Do you want me to solve an example from chapter 3, or do you want me to solve an example from the rest of chapter 2, the perifocal frames?
Will chapter 3 be on the exam?
Yes, but we have already solved an example from it, didn't we?
We did 2.7 or 2.8.
No, we solved. We did 3.2, I guess. Yeah, 3.2. We did the 3.2.
Chapter 3 mainly the Newton method stuff.
Yes. That's it.
I'm good either way.
You won't calculate any Lagrange constants on an exam. I just wanted to. I included them in the lecture because I wanted to make sure you are exposed to them. Right? Because there's no point in calculating them by hand. You have to write a MATLAB code and all those. Let's go with chapter 3. But make sure you understand the perifocal frames as well. Chapter 3. This is example 3.5, which I think I did not include on the PDF file that I gave you. But I will update the PDF file to include this example. And if all of these are book examples, so you can always go back and read the book. But if you don't have the book, I will upload the examples with their solutions. So this is example 3.5. We are told a geocentric trajectory has a perigee velocity of 15 kilometers per second. So VP is 15 kilometers per second. And a perigee altitude of 300 kilometers. You want to find the radius and time when through an anomaly is 100 degrees. And we want to find the position and the speed 3 hours later. Okay. Let's answer the first part, part A, first, of course. What do we have here? We have the perigee velocity at perigee and apogee. We only had, the idea was that VR is 0. So perigee is actually the azimuthal velocity at perigee, right? And the azimuthal velocity and the apogee. And we can, based on this, we can find the perigee radius, 300 plus 6,378 kilometers. Just make sure whenever you were given altitude, that's the distance from the surface of the Earth. You have to add the radius of the Earth to be able to use it. And we had the relationship between angular momentum and the azimuthal velocity, which in this case is going to be your perigee radius multiplied by the perigee velocity. If you plug in all of the values you have, you are going to get 100,170 kilometers squared per second. Okay, how can we find eccentricity, or can we find eccentricity here? We have R of P, theta is 0, right? H squared divided by mu, 1 plus E, right? Perigee, right? We have mu, we have H, we have R of P. We can find eccentricity to be 2.7696. Do you remember how did we find the true anomaly of the asymptote, or theta infinity?
That's different than mean anomaly?
Yes. That's the true anomaly of the asymptote. You don't need to go back to your notes. Just think about it. We want to find the true anomaly at the asymptote. What would be the R at the asymptote? What's that?
That's not right.
So this is your hyperbolic trajectory. It has an asymptote, right? I want to find the R at this asymptote. Infinity, exactly. So how can we get the R to be infinity? This is for perigee. The original orbit equation is, right? This is infinity. What should happen to this? This has to be equal to 0. Right? 1 over 0 is infinity. Exactly. So your cosine of theta infinity has to be negative 1 over E, right? Or theta infinity, which is the true anomaly at the asymptote, has to be cosine 1 over E. We have calculated the E. We can calculate the true anomaly at the asymptote, which is 111 which is going to be 111.17 degrees. Is this a smaller or larger than 100? Larger, which means that this is a true anomaly. This is a possible true anomaly on this trajectory. Okay? Because it is smaller than the infinity true anomaly, right? So, and we want to find the radius at this true anomaly. How can we find radius at this true anomaly? We have the orbit equation, h mu theta e. We can find the radius to be 48,000, 48,497 kilometer. Okay, what is the next step here? How can we find time? That, no. That was the capital T. That was the period, right? How can you relate that? What is the relationship between time and period? But we had a specific equation. We had a specific set of solution that we followed. It is a hyperbolic trajectory, right? And we are running out of time. It's a hyperbolic trajectory, right?
Use the time-based radius thing. The r theta equals a square root of 3 minus 2 RT over a.
Let's see if we can use this. What was the eccentric anomaly for a hyperbolic trajectory? F, right? We had this equation, tangent of f divided by 2 is equals to a square root of e minus 1, e plus 1, right? Tangent of theta over 2. We have the e, we have theta, we can find the eccentric anomaly. Then we had a relationship between this eccentric anomaly and the mean anomaly, right? M of h is equals to e hyperbolic sine of f minus f, right? Do we have the f? Yes. Plug it in, hyperbolic sine calculated. We have the e. We can find the mean anomaly of the hyperbola. Then we had the relationship between the time and the mean anomaly. T would have been h cubed mu squared 1 over e squared minus 1 3 by 2 m of h. You have calculated time here. So we didn't remember this?
I think, I do remember that in the notes whenever we went over the capital.
It's in the notes. I didn't know that's where it applied.
Yeah. So whenever I ask you to find a time, keep thinking of these equations. If it's a hyperbolic trajectory, if it's an elliptical trajectory, we had E and M of E, right? And on the next step, I've given you the time. That's 3 hours, right? 3 hours after the passage from the, let's see, 3 hours after this time. Okay, that's going to become a problem. Let me explain this and then we'll go from there. So next part is asking us to find the position. So to go the other way around after 3 hours. But this is 3 hours after this time, whatever time that is. Let's do this. I won't give you these type of problems in the exam 2. We'll review this. On the last day, you will get it. This type of, I will give you this type of problem on let's actually make it easier. Exam 2, just chapter 1 and 2.
Oh, that's yeah,
Okay.
that's awesome.
Okay.
Yeah. If I don't know, I feel like I can worm my way around it.
Okay.
I'll bring my copy next time.
That's just an extra. I don't need it.
Okay.
You can have two. Give it to your friends.
My next friends won't like that.
Why not?